Tip a jar of honey, and it crawls. Tip a glass of water, and it is gone in an instant. Same gravity, same pull, so what makes one liquid refuse to move? The answer is viscosity. We will build it from the ground up. What it is, where Newton's law comes from, and why engineers use two different numbers. Honey, water, both are liquids, but tip them over, and they behave completely differently. Honey is thick and sticky. Its resistance to flow is very high. Water is thin and runny, low resistance, and it flows easily. That property is viscosity. So where does it actually come from? Zoom in, all the way down to the molecules. In a thick liquid, molecules sit close together, with strong forces of attraction between them. When one layer tries to move past another, those attractions pull back. There is very little relative movement. That is more viscosity. In a thin liquid, the attractions are weaker. Layers slide past each other easily. That is less viscosity. So viscosity is an internal friction, a viscous force that resists relative movement inside the fluid. Now let us measure it. Place a liquid on a flat, stationary surface. Right at the wall, the fluid does not slip. Its velocity is exactly 0. This is the no-slip condition. Add a second plate on top, and drag it sideways with a force F. The layer touching the moving plate travels at the plate's speed. The layer at the wall stays at 0. Every layer in between slides over the one below and drags it along, so the velocity rises steadily across the gap. The force, divided by the plate area, is the shear stress, tau. The change in velocity divided by the gap is the velocity gradient, or shear rate. Newton found that these two are directly proportional. Tau equals mu times du by dy. Newton's law of viscosity. Mu is the constant of proportionality, the coefficient of viscosity, or dynamic viscosity. Rearranged, viscosity is shear stress divided by shear rate. Its units are Newton seconds per square meter, the same as Pascal seconds, or kilograms per meter second. In the CGS system, the unit is the poise. 1 poise equals 0.1 Newton seconds per square meter. Water at 20 degrees Celsius is 1 centipoise. That is the reference every viscometer is calibrated against. Now, a second definition. Divide dynamic viscosity by density, and you get kinematic viscosity. Why? Because some flows are not pushed by a machine. They are driven by the fluid's own weight. Two oils with the same dynamic viscosity, but different densities, drain at different rates. The heavier one pulls harder on itself. Kinematic viscosity captures that. Its units are square meters per second, or the stoke. 1 stoke is 1 square centimeter per second. Use dynamic viscosity when a machine supplies the force. Mixer torque, pump power, coatings and inks. Polymer melts. Use kinematic viscosity when gravity supplies it. Capillary viscometers, lubricant grades, and Reynolds number. One last thing, and it matters more than anything else on this list. Viscosity changes with temperature. Heat a liquid, and its molecules gain energy. The forces of attraction weaken, layers slide more freely, and viscosity falls. Water drops from 1.79 millipascal seconds at 0 degrees to 0.28 at 100. So a viscosity number without a temperature is meaningless. Always state both.